Hello and welcome to an episode that deals with use of video broadcast, video standards, NTSC, PAL, SECAM and HDTV. Television pictures, serials and documentaries educate us, provide information and entertain all. The world has become a global village. How does television picture reach us? How do we find the same picture quality across various receivers? Today we shall discuss various television standards in this episode. The subject expert today is Saba Parveen and I am Sakshi Mandwal. Saba Parveen is Assistant Engineer in Electronic and Telecommunication at Anwar Jamal Kidwai Mass Communication Research Center, Jamia Millia Islamia. In today's session, we shall cover some basics of television like frame, lines, timing, aspect ratio, etc. Adding color to monochrome television and properties of color. World television standards. Digital broadcasting. Television broadcast commenced approximately 60 years ago. The knowledge gained over the years has helped evolve better standards. As a result, the US, which saw the birth of widespread commercial television broadcasts, evolved the first system, which predictably is also the most primitive. Before we consider different television systems, we need to take an understanding of the basics of television transmission. Frame. A television transmission consists of a series of rapidly changing pictures which convey to the viewer an illusion of continuous motion. The pictures need to flash at a rate of more than 16 pictures per second as per the perception of the eye into seeing continuous motion. Each of these rapidly changing pictures is termed frame. Typically, a television transmission consists of either 25 or 30 frames per second. This is shown in the figure. Lines. Each picture consists of several closely spaced lines. The lines are scanned, written from left to right and from the top of the screen to the bottom of the screen. Typically, a TV picture consists of 525 or 625 lines. In view of the large number of lines, if all lines were written one after the other on the screen, the picture would begin to fade at the top of the screen by the time the last few lines at the bottom of the screen are written. To avoid this, the first frame carries only the odd numbered lines, that is, line numbers 1, 3, 5, etc. The next frame carries only even numbered lines, for example, line numbers 2, 4, 6, etc. In this manner, successive frames carry the odd and even numbered lines. This provides a uniform intensity to the picture and is called interlacing and indicated in the figure. Timing. TV receivers require a source to time the rapid succession of frames on the screen. Designers decided to use the main power supply frequency as source for two reasons. The first was that with the older type of power supply, non-SMPS, you would get rolling hum bars on the TV picture if the main supply and power source were not at exactly the same frequency. The second was that the TV studio lights, or for that matter, all fluorescent non-incandescent lights flicker at the mains frequency. Since the flicker is much higher than 16 times per second, the eye does not detect it. However, this flicker could evolve into an extremely pronounced low-frequency flicker on TV screens due to a beat frequency generated between the light flicker and the mains frequency. This would have made programs difficult to view, particularly in the early days of development of TV receivers. There are two mains power frequency widely used around the world, 50 Hz and 60 Hz. This immediately divided the world TV system into two distinct camps, the 25 frames per second camp, 50 Hz, and the 30 frames per second camp, 60 Hz. Later, the 60 Hz camp made a small adjustment and changed the field rate to 59.94 Hz when they added color to the signals. The issue of field frequency remained sufficiently deep-rooted in both TV standards that the vested interest remained long after the original technical justification had gone. The biggest compatibility problems between TV standards remain related to the field rate. These are also the hardest problems to solve. Aspect ratios. The aspect ratio is the proportion between the width and the height of a picture. It is often expressed in the W:H format, where W is the width and H the height. For example, a 16:9 aspect ratio means that for a width of 16 units, the height must be 9 units. Although the number of scanning lines may have varied, until recently all television systems had a 4:3 aspect ratio. Use of video broadcast video standards. Aspect ratio uses TVs 4:3, 1.33:1, standard channels, old TVs. 16:9, 1.77:1, HD channels, the majority of HD TVs. 21:9, 2.35:1, most movies, very few TVs. The most common aspect ratios in the video industry. In the picture here, the wider area just inside the blue borders represents the 16:9 ratio used in HD TV. Compared to the 4:3 ratio, this aspect ratio is closer to the wider perspective of normal human vision. Most televisions and computer monitors currently available have an aspect ratio of 16:9, which fits perfectly the high-definition television shows. However, movies are usually filmed with a ratio of 21:9, which results in black bars at the top and bottom of the picture. To fix this, some manufacturers are producing televisions with a 21:9 format, also called cinema wide. The table shows the most common aspect ratios. Adding color to a monochrome system. Modern color television has resulted from the addition of suitable techniques to existing monochrome systems. The transmission, reception and processing of black and white signals require three separate items of information: the video information and the synchronizing information for two-dimensional scanning. Color required three further types of information. It is necessary to determine luminance, hue and saturation of any color. Fortunately, monochrome systems are luminance only systems and they can supply the luminance information. This leaves two extra items of information to be transmitted and received, which when suitably processed can determine the hue and saturation encountered during scanning. Apart from the obvious difficulties, some severe constraints exist on the addition of color information. It must not require extra channel space. There must be no interference between the existing luminance information and the added information. It must be totally compatible. That is, a monochrome receiver must display a color transmission in black and white, and a color receiver must be capable of displaying a monochrome transmission in black and white. The properties of color. Each picture element in a color has three basic properties. In objective terms, they are luminance, hue and saturations. The corresponding perceptual terms are brightness, color, purity. The term luminance has approximately the same meaning in color television as in monochrome. Like a monochrome system, a color television system must have the capability of transmitting the luminance of each picture element. But in addition, it must transmit and reproduce each element's hue and color purity or saturation. World TV standards. A number of TV standards now coexist worldwide. A TV program produced in one country can't automatically be viewed in many other countries without converting it to a different technical standard. These technical differences relate to both incompatibilities in equipment and in the approach to broadcasting the audio and video signals. Some 14 different SDTV standard definition broadcast TV standards have been used at different times throughout the world. The present color television systems are fundamentally based on the work of the National Television Systems Committee (NTSC) in the USA in 1951 to 1953. The committee, formed by some of the leading research laboratories, had the aim to evolve a color television system that would be compatible with the existing black and white television system. The black and white receivers must be able to receive the color transmissions, and the color TV receivers must be able to receive the black and white transmissions. This required that the additional color information sent in the color TV system must be accommodated in the same channel bandwidth carrying the black and white information. The worldwide color television broadcast works on three basic standards: NTSC, National Television System Committee; SECAM, Sequential Color and Memory; PAL, Phase Alternating Line. National Television Standards Committee (NTSC). In the NTSC system, requirements were indigenously fulfilled, albeit in a complicated way. That is why some parts of the system appear rather circumstantial. The ideas used to make the system compatible are indeed ingenious and fascinating, even in retrospect today. It may be noted that if television had started with color right in the beginning, the system would have been much simpler. In the NTSC system, the three primary color signals R, G and B from the three camera tubes are combined to obtain the luminance signal, which is useful for the black and white compatibility. Two more signals, called the chrominance signals, representing the hue and saturation of the color, are derived from these RGB signals. These chrominance signals with limited bandwidth modulate an auxiliary carrier near the upper end of the video band. This subcarrier is so chosen that the spectral energy of the sideband of the carrier can be interleaved in the gaps existing in the black and white spectrum. The combined video signal is then transmitted on the standard TV channels. At the receiver, a corresponding reverse process takes place to obtain the RGB signals that control the beam currents of a tricolor picture tube. The NTSC system is highly sensitive to phase errors in the subcarrier containing the color information. Modified systems based on the same theoretical considerations of the NTSC, but avoiding the great phase sensitivity, was introduced in France under the name SECAM system in 1958, while in Germany the PAL system was developed, in which the phase errors are cancelled by alternating the phase for every other line. The various parameters of the NTSC standards are: National Television System Committee, lines or field 525 by 60, horizontal frequency 15.734 kHz, vertical frequency 60 Hz, color subcarrier frequency 3.579545 MHz, video bandwidth 4.2 MHz, sound carrier 4.5 MHz. The PAL standard. To overcome the limitations and shortcomings of NTSC standard, PAL standard was developed. This system of phase alternation by line, PAL, put forward by Professor W. Bruch of Telefunken in West Germany in 1959, is very similar to the NTSC, except that the color subcarrier phase is reversed on every other line and simple color difference signals RY and BY, called V and U signals, are used. These modifications make the system less sensitive to subcarrier phase errors. phase errors in a system can arise at a number of places in the studio chain and the transmission path. Since colors are represented by the phase rotations of individual frequencies of the color signal spectrum relative to the phase of the subcarrier transmitted in the form of the burst, cause color shifts in the reproduced signals. In the NTSC receiver, a phase correction adjustment may have to be provided to remove the color shift. In the PAL system, the U and V signals are transmitted as simultaneous pairs of chrominance components in the form of amplitude modulated sidebands of a pair of suppressed subcarriers in quadrature as in the NTSC system. The phase of the V signals is, however, reversed on alternating line. This causes alternating phase error reversal in the color subcarrier vector, tending to cancel out the effect of color shifts on the human eye. The various parameters of the PAL standard are as phase alternating line, system PAL, PAL-N, PAL-M. Line or field 625 by 50, 625 by 50, 525 by 60. Horizontal frequency 15.625 kHz, 15.625 kHz, 15.750 kHz. Vertical frequency 50 Hz, 50 Hz, 60 Hz. Color subcarrier 4.433618 MHz, 3.582056 MHz, 3.575611 MHz. Video bandwidth 5.0 MHz, 4.2 MHz, 4.2 MHz. Sound carrier 5.5 MHz, 4.5 MHz, 4.5 MHz. The SECAM standard. The phase of the subcarrier in the NTSC system carries the hue information, and any error in the phase of the subcarrier in the transmission process introduces serious errors in color reproduction. To avoid this problem arising out of the subcarrier carrying both the chrominance signals simultaneously, HD France proposed the SECAM, Sequential Color a Memoir, system in France in 1958. The system rested on the same theoretical principles of the NTSC system, but the two chrominance signals are transmitted on alternate lines in sequence 4. As a result, half of the color information is lost on each line. This reduces the color sharpness in the vertical direction. This, however, is of not much loss as far as the perception of the eye goes. In the NTSC system, although the horizontal color resolution is reduced by limiting the bandwidth of the I and Q signals, the resolution in the vertical direction is maintained to the full as determined by the number of scanning lines. In the SECAM system, the color resolution is reduced in the vertical direction also within tolerable limits of the eye. In the SECAM encoder, the RY and BY signals band limited to 1.5 MHz are applied to the FM modulator alternately via an electronic commutator. The various parameters of the SECAM standard are sequential color avec memoire or sequential color with memory. System SECAM BGH, SECAM DKK1L. Line or field 625 by 50, 625 by 50. Horizontal frequency 15.625 kHz, 15.625 kHz. Vertical frequency 50 Hz, 50 Hz. Video bandwidth 5.0 MHz, 6.0 MHz. Sound carrier 5.5 MHz, 6.5 MHz. Digital broadcasting. The world moves to DTV. By 2014, the majority of countries in the world had switched from analog to digital broadcasting. Digital TV has numerous advantages. It uses a more efficient transmission technology, allowing for improved picture and sound quality. In addition, digital signals provide more programming options through the use of multiple digital subchannels, channels of information within the basic broadcast signal. Compared to analog signals, digital broadcast signals react differently to interference. Common problems with over-the-air analog television include ghosting of images, seeing multiple faint images at the same time, note photo, noise or snow because of a weak signal, etc. Changes in analog signal reception result from factors such as a poor or misdirected antenna and changing weather conditions. But even under these conditions, an analog signal may still be viewable and you may still hear the sound. Digital television transmissions are more demanding. The nature of digital TV results in a perfect picture initially until the receiving equipment starts picking up interference or the signal is too weak to decode. With poor reception, some digital receivers will show a blocky video or a garbled picture with significant damage. Other receivers may go directly from a perfect picture to no picture at all. This phenomena is known as the digital cliff effect. The first country to make a complete switch to the digital over-the-air terrestrial broadcasting was Luxembourg in 2006. Shortly thereafter, the Netherlands made the switch. Finland, Andorra, Sweden and Switzerland followed in 2007. In June 2009, major broadcast stations in the United States switched to DTV. Some countries don't plan a complete analog to digital transition until around 2020. As shown in the illustration, there are 4 basic international standards for digital broadcasting. The United States and Canada use the NTSC, Advanced Television Systems Committee standard. One of the major differences between analog and digital TV is the number of horizontal scanning lines that make up the picture. The greater number of lines, the more picture detail is possible. The table summarizes this. Standards: SD-TV analog, HD-TV digital. Total lines: 525, 1125. Active lines: 480 to 486, maximum visible on the screen. 1080, maximum visible on the screen. Sound: 2 channels, stereo. 5.1 channels, surround sound. Max resolution: 720 into 486, 1920 into 1080. As you can see, the NTSC standard is capable of 16:9 images up to 1920 by 1080 pixels in size and resolution. This is more than 6 times the display resolution of the analog standard. In addition, many different image sizes and line standards can be supported. These include standard definition 480i, interlays that are compatible with existing NTSC sets; enhanced definition 480p, progressive, about the same quality as current DVDs; high definition 720p, high definition 1080i, the highest definition currently being broadcast; high definition 1080p, Blu-ray equipment and a few cable operators. Differences in detail. Compare the screen enlargements shown here that represent HDTV on the left and the standard NTSC systems on the right. When projected on a 16:9 foot screen and observed from normal viewing distance, the picture detail in good 1080p HDTV systems appears to equal or better than attained by projected 35 mm motion picture film. HDTV can be converted to film and projected in a theatre without most patrons realizing they are seeing video. The enlarged illustrations on the left above show the relative pixel detail of SDTV and HDTV. The illustrations assume a 40-inch TV screen. SDTV produces an image with about 2 lakh pixel picture points. HDTV increases that by a factor of about 10 to 2 million pixels. Ultra high definition. There are now 2 additional levels of sharpness beyond HDTV. In 2013, ultra high definition sets and monitors started appearing. These are divided into 2 levels: 2K with 2048 pixel lines and 4K with 4096 pixel lines. Pixel stands for pixel element. However, it's been shown that average TV viewers can't discern the difference between them and HD TV at normal TV set viewing distances. It is only when 2K and 4K images are projected on a large screen that the difference in detail becomes obvious. Converting widescreen formats. Production facilities make the conversion of 16:9 HDTV or DTV images to the standard 4:3 aspect ratio in the same way they convert widescreen films to SDTV. Three approaches are used. First is when the conversion involves cutting off the sides of 16:9 image to a narrower 4:3 size. We refer to this as an edge crop or 4:3 center cut. If we shoot the original HDTV or DTV or widescreen film with the narrower 4:3 cutoff area in mind, losing the information at the sides of the picture should not be an issue. This is the area on each side of the red box in the photo, which, as noted, is referred to as a center cut of the full 16:9 raster. We refer to the procedure of keeping essential subject matter out of the cutoff areas as shoot and protect. Second, the entire production can go through a process called pan and scan. In this case, a technician reviews every scene and programs a computer-controlled imaging device to electronically pan the 4:3 window back and forth over the larger widescreen format. The red arrows in this illustration suggest this panning movement. In the above picture, cutting off the sides would not be an issue. But what if you had the two parrots talking to each other from the far sides of the screen? Finally, if the full HDTV or DTV frame contains important visual information, as in the case of written material extending to the edges of the screen, panning and scanning will not work. In this case, a letterbox approach can be used as shown here. But you can see the problem. The result is blank areas at the top and bottom of the frame. Often, we reserve the letterbox approach for the opening titles and closing credits of a production, and pan and scan is used for the remainder. There is another way of handling the 16:9 to 4:3 aspect ratio difference, especially for titles and credits. You've probably seen the opening or closing of a film on a television horizontally squeezed in. We refer to this optical technique as anamorphic conversion. The effect is especially noticeable when people are part of the scene, people who, as a result, suddenly become rather thin. Compare the two images above. Note how the bird in the squeezed 4:3 ratio on the right seems to be thinner than the bird on the left. Another way of visualizing the major SDTV to HDTV and HDTV to SDTV conversion approach is illustrated here. Recap. In today's episode, we discussed some basic fundamentals like frame, lines, timing, and the aspect ratio of the television. Besides the basic fundamentals, we also discussed the world television standards, including the digital broadcasting standards. Hope you enjoyed this episode. That's all for today. Thank you and goodbye.